Good morning, everyone. So we are finished with all new material. Your fourth test is this Sunday/Monday, so make sure to take it. So hold on one second, pulling up our syllabus. Yeah, so your exam, I guess I'm selfishly looking at it on my iPad. I guess I can pull it up for you guys as well. Don't want that. All right, so we're sitting right here, specifically here. So today we're going to do some final review stuff. If you have questions on specific things, or you want me to go over certain things, you gotta let me know. Your last test on chapters 11, 13, and 14 will be right here, that Monday Sunday/Monday. And then next week is the final exam. So I set the final exam for Thursday, Friday of the week, just so you would have the whole week to study, to give you the most amount of time. If for whatever reason, like all of your finals happen to be on Thursday, Friday, and you'd like to pop in there early, I can make an exception, but you got to let me know. Otherwise, if it's not an issue for you, just take it on Thursday or Friday. Yeah, so we really aren't going to meet next week at all. I will be available, so I'm around. I'll be available through email, and if you need like one-on-one sessions or anything like that for studying, I'm totally available for that. But we won't have like a formal meeting time, just so you know. So let's get started doing some review. So I want, you guys got to tell me what you want me to go over. So if there's any, throw it in the comments. Something you feel shaky on, even if it's as broad as like a concept, like I'm not good with nomenclature. I can go over that, but you gotta let me know. Let's see what we got. First one up. Will we have to name any acids? You'll have to name like basic acids. So things like binary acids, which are acids that are combined with just one other thing. So like HCl, HBr, HI. These would be things that you would want to name. Remember, when they're binary, so they're just hydrogen with one other thing, we use the prefix hydro. We take the root of the second thing, chlor, we ick it, and then we add acid. Hydrochloric acid. So this thing here would be hydrobromic acid. This one sounds kind of funny. Hydroiodic acid. This one here, this is a diprotic acid. There's 2 hydrogens for every 1 sulfur because sulfur has a charge of 2 minus. This one is hydrosulfuric acid. They use the entire sulfur name. It's not hydrosulfic acid. Okay. But that's really going to be the extent of naming acids for y'all. Other questions? And feel free to pull out your notes right now. Pull out your big binder of notes, or your like 3 scrap pages of notes on the semester, and flip through it and look and say, I'm not good with this. I am good with this. We'll tell you right now, the final is very nomenclature heavy. So there are not all the questions are nomenclature, obviously, but there is a disproportionate amount of them that are naming in nomenclature. So if anybody wants to do some naming, I'm always up for that. You gotta tell me though. Let's do it. Awesome. Harley is holding the class together today. Lyric says, yeah. Okay, cool. So let's do some nomenclature. So I'm going to give you a bunch of names and I want you to write the formula, and then I'm going to give you the formulas and I'm going to have you write the names. You have to, I'm going to give them all mixed up. Okay. So you're going to have to pick out like what technique you want to use for which. So let's start with, so you're going to need to name these. And then I'll give you some names and you write the formula. Okay, so we've got a CaCO3, an Na2S, an FeO2, an HCl, an NO2, an NiPO4. And on this column over here, we've got cobalt 2 sulfate, silver hydroxide, dicarbon disulfide, lithium oxide, manganese 3 oxide, sulfur trioxide. So I want you to make these ones look like these and these ones to look like these. So I'm going to give you all 5 to 10 minutes, somewhere around there. Yeah. Obviously, while you're working on them, if you have a specific question, ask me. But I'm going to give you a little bit of time here to work through these. Okay, so we'll start chipping away at these. So when looking at a formula and you want to determine the name, you first got to decide what is the thing and what is it containing. So this is an ionic compound. So if you want, you can even put a little note next to it here that says that this is ionic. Come on. And it's specifically a type 1, meaning that this has a predictable charge. Okay, so we don't need any sort of Roman numerals. There's also a polyatomic ion in there. So if it's ionic, we list the name of the metal first. So this is calcium. I don't need a Roman numeral because calcium's charge is always a 2+. Where is that 2+ coming from? Go to your formula sheet. It's in column 2. We had put a 2+ above that. Just remember that. And then this mess here is carbonate. If you ever get to a place where you're trying to name something and you're like, it's not following the rules. What is all this? There's like 3 different types of atoms and it's confusing. It's a polyatomic ion. So this thing here is carbonate. We just list the name carbonate. Calcium carbonate. This one here is also ionic. It's also type 1. So sodium has a predictable charge. So I can write the name sodium. Sodium doesn't start with an N. Sodium. I don't need to specify how many I have or anything like that. All I do is write the name of the metal, and then I write the name of the nonmetal, and I ide the nonmetal. We don't ide our polyatomic. We leave that true. So sodium sulfide. This one here, this is ionic. This one's a little different than the previous 2 though, because this is a unpredictable charged or a type 2 ionic metal. So I'm going to say iron. Put in, I like to put in my parentheses and come back to it. This is oxygen, so we will ide it, oxide. So this is some sort of iron oxide. Now we've got to specify what the charge is on it. So in order to do that, put a little line between these. The total charge on this whole molecule has to equal 0. So whatever the negative charge is from the anion, it has to equal the positive charge of the cation. I don't know the cation because it varies in charge. So I go from what I do know for sure to get what I don't know. So what I do know is that oxygen is always a 2- charge. And I have 2 of them. So I need to multiply this by a magnitude of 2 for an overall -4 charge. If this is -4 over here, what does this have to be to balance that out? It has to be a +4. So this is going to have a Roman numeral 4 for it. This will be iron 4 oxide. This next one down here, it's got that hydrogen written in the front. So this is an acid. It's a binary acid. It's just mixed with one other thing. So we're going to say that this is hydrochloric acid. Sorry, I messed my wrist up a little bit. So I've got it wrapped on my writing hand. My handwriting is especially horrible today. So if you have any questions or something isn't clear, let me know. All right, I've got NO2. So this is different than the previous ones in that it is not ionic. It is molecular, meaning that it's a combination of nonmetals. So this is where I use prefixes. I have to specify how many of each I have. The reason is because you could have nitrogen come together with 2 oxygens, or you could have nitrogen come together with 1 oxygen, or you could have nitrogen come together with 6 oxygens, or you could have 3 nitrogens come together with 2 oxygens. There's so many different combinations with nonmetals that you got to let the reader know how many of each you have. So I have 1 nitrogen. I don't need to say mono if it's on the first guy. So I'm just going to say nitrogen. I do need to specify how many I have on the second one. So there's 2 oxygens. So that's going to be dioxide. And we do IDE, the end of it. Nitrogen dioxide. This thing down here, This is ionic. This is a metal, but it's a type 2. So I need a Roman numeral. So this is going to be nickel with some sort of Roman numeral. And then this thing here is phosphate. It's a polyatomic ion. Phosphate. I don't have to change the ATE to an ITE or anything like that. Leanna asks, let's pause for a second and go back to the previous one. Leanna asks, isn't NO2 nitrite? No, it looks like it though, doesn't it? But it doesn't have the charge in the upper right-hand corner. So there is a difference between there's a difference between this and this. This is nitrite. This is nitrogen dioxide. Very, very good question. Ugh, come on. I don't know why it's not letting me write right there. Nitrogen dioxide. Okay, same thing with if you were to see this SO3 versus SO3 2 minus. This is sulfur trioxide. This is sulfite. Okay, the charge makes it the polyatomic ion. Polyatomic ion has to have a charge to it. Does that make sense? Great. Okay. Good question. I want you gone. So let's finish up this guy here. So that looks like it's nittle. Try and write that a little better. Nickel phosphate. So we need to figure out what the charge is on this nickel because it's a type 2. So I'm gonna just kind of put a line between my metal and my non-metal stuff. Phosphate is a polyatomic ion that always has a 3- charge. I only have one of them, so I just need to take the 3- times 1. So nickel will have to be a 3+ to counteract that. So it'll be nickel 1, 2, 3, nickel 3 phosphate. Any questions on those? Or any ones that you want me to do while we're on this side, you want me to do another example of, because you're like, ooh, I'm real shaky on, you know, the varying charges or the acids or whatever. And if not, that's fine. We'll just move to the other column. But I just want to make sure that you've got that. If you get this conceptually, right? And then also this side, that is like 99% of naming. Obviously there'll be different elements, but the concepts really covers everything. Let's see. The one like iron and nickel. Okay, Gabriella, let's do another iron and nickel one. We'll pause and come back to that. So let's do a little subset here of just varying charges. So we've got Fe2O, FeO, and no, I don't want to do that. Pb2SO4 and PbSO4. So I'm going to do these sort of groupings. just so we can see how things vary and change. I'm gonna throw another one down on this bottom one here too, just to make it look really scary, but it's not really scary. Let's do PB SO42. Okay, so give those a shot. I'll give you 5 minutes and then we'll go over. I'll give you 3 minutes and then we'll go over those. So at least try them. Okay, so the reason I did these is so that you can see how they're kind of a group of compounds. These are all iron oxides in some capacity. So iron something oxide. This is also an iron oxide. My guess is that going from here to this part isn't difficult. It's that the charge part that we get a little confused on. So I'm going to cut this thing in half. I've got my nonmetal and my metal. My metal varies in charge, so I have to go off of what this tells me. So this tells me that there's a 2- charge. Oxygen always has a 2- charge. There's only one of them. So it's a total negative charge of 2-. So my total positive charge has to be a 2+. Now the thing is there's 2 irons on this side. So each iron will contribute a +1 to give you the overall 2+, or you need to take this number and you need to divide it. So if you're going from here up to here, you have to multiply by your subscript. If you're going from here down, you have to divide by your subscript. So in here, this would be iron 1 oxide. This guy, oxygen is a 2- charge, and there's only one of them. 2+, and there's only over 1 iron. So this is iron 2 oxide. So close, but they will yield a different formula. These are all, this is lead, and this thing is sulfate. So they're all lead sulfate in some capacity. The thing that changes on these is that we got to figure out the charge on the lead. So I'm going to put a line through each of these to separate my metal stuff from my non-metal. Sulfate, polyatomic ion with a 2- charge. So this over here has to have a 2+ charge. But remember, it's divided by the number of atoms you have. So in this case, I have 2 leads for an overall 2+ charge. 2 divided by 2 will give me lead 1 sulfate. This one here, sulfate has a 2- charge. So this side has to have a 2+. How many leads are there? There's only 1. So it's just going to be lead 2 sulfate. This one here, I have a 2- charge, and how many are there? There's 2 of them. So times 2, which would give me a 4- charge. So that means this is a 4+ charge. So this would be lead 4, because there's only 1 lead to distribute it over. Questions on those? Good. All right, I'm going to move forward. Whoa. Hello. No, we don't want you yet, pen. All right, let's go right here. So some people find this way easier. Depends. Different people kind of like going in different directions. I find this one easier. I feel like it's easier because it gives you all the information, so you don't have to like find the charge. It tells you the charge. Okay, so again, you have to ask yourself, what is this? This is a metal and a non-metal. Specifically, it's a metal with a varying charge and a polyatomic ion. When you have ionic names, you have to flip-flop charges to get the correct formula. So cobalt, so I'm going to write the symbol for cobalt. Its charge is 2+. You don't go to the periodic table for the varying transition metals. Sulfate is SO4, and it's got a 2- charge. And if you want, you can sort of circle it so that you remember to keep that as a unit. This is a 2 and a 2. So when I flip-flop charges, each one will have a subscript of 2, and we can reduce that. So this becomes COSO4. Silver hydroxide, silver, Ag, it does sit in the transition metal area, but it has a predictable charge of +1. So go to your periodic chart. Remember that aluminum is a 3+, go down and to the left to zinc. That's a 2+, go down and to the left to silver. That's a 1+. Hydroxide is OH with a minus charge. Flip flop, this is a 1-to-1. I'm just going to go AgOH. I don't need to put my polyatomic ions in parentheses if I only have one of them. Okay, dicarbon, disulfide. I start seeing prefixes. I know that those are 2 nonmetals, and I need to specify what the prefixes are as a subscript. Don't flip-flop. It wouldn't really matter because this is di and di, but don't flip-flop. You only flip-flop with metals and nonmetals. So this is carbon with a 2 and sulfur with a 2. And that's it. These are super easy. I like these ones. Lithium oxide, metal, non-metal, metal with a predictable charge. So Li has a plus charge, oxygen has a 2- charge, flip-flop, Li2O. The 2 drops down to lithium's subscript. The 1 from the lithium drops down to oxygen's subscript. Manganese 3 oxide. All right, so manganese a lot of times gets mixed up with magnesium. Those are not the same. So don't write Mg for this. This is Mn. So we have Mn, and it tells us the charge is a 3+. The oxygen O always has a 2- charge. Sorry. So flip-flop, we get Mn2O3. Last one here, sulfur trioxide. Sulfur and trioxide are both nonmetals, so I'm just going to write the prefix as the subscript. So sulfur doesn't have one there because it's mono on the first, so we can just write sulfur. Trioxide means that I have O with a 3. Any questions on those? And or let's move on to something new if there's stuff that you want to ask about, other questions. You got to let me know. So hopefully that helped with most of chapter 5, which is the nomenclature chapter. If you're like, I got this, you should be good for the final. Lewis diagrams, perfect. Okay. So I'm going to do it for H2O, water. So I'm going to do the Lewis dot structure. I'm also going to do its electron geometry, its molecular geometry, and whether it's polar or nonpolar. So H2O, if we're trying to do its Lewis structure, its Lewis dot structure, the first thing I need to do is count up how many valence electrons I get to use in my structure. So each one will contribute a certain number of electrons depending on what column it's in. They contribute those electrons, but at the end of the day, they want either a duet if they're hydrogen or helium, or they want an octet, pretty much if they're everything else. So hydrogen brings 1 valence electron, but I have 2 of them. Okay, so I need to multiply that by 2. Then I need to add what oxygen brings. Well, oxygen is in column 6. So it brings 6 valence electrons. So this gives me a total of 8 electrons to mess around with. So I can't have more than 8 electrons. I can't have less than 8 electrons. And no one owns these electrons. This is the total amount. They just need to be distributed in a way where we fulfill octets and duets. So I need to make a skeletal structure where this thing looks balanced. So I wouldn't do this. I wouldn't do H, H, O. That looks weird for many reasons. One is that hydrogen is a terminal atom. It likes to be on the end because it only wants 2 electrons. Also, we like to create sort of a balanced structure. So oxygen in the center and 2 hydrogens on the side are going to look much better. So first thing you do is draw out a structure that looks relatively balanced. And then you bond them together, fuse them together with a single bond. Now on the board currently I have 4 electrons, 1, 2, 3, 4. I need 8 electrons on the board. So I first make the outer guys happy and then I work to the inner one. Always do that, always go from the outside in. Now in this case, these hydrogens are already happy because they have access to 2 electrons. So the remaining electrons I'm going to need to put on the central atom. All right. So here is our Lewis dot structure. There are 8 electrons on the board. Hydrogens are happy. Oxygen has access to 2, 4, 6, and 8. He is also happy. So when talking about the electron geometry, this is referring to how the electrons are spread out around the central atom. So we include all electron groups on the central atom. Remember, an electron group is a single bond. An electron group is a double bond. So a double bond would count as 1 electron group or 1 electron domain. A triple bond would count as one electron domain, and a lone pair of electrons would count as one. So here's 1, 2, this pair is 1, and this pair is 1. So we have 4 electron groups here, 4. So 4 electron groups is tetrahedral. Now the molecular geometry, if you have lone pairs on the central atom, you are going to have a different molecular geometry from your electron geometry. So what we need to do is take our tetrahedral shape, or that sort of little pyramid shape, and you need to rip 2 of the atoms off the end, but the electron groups are still there to affect the other ones. So what is the remaining shape? In this, it will be bent, or sometimes it's called V shape. As far as polar or non-polar, this is going to be polar. Anytime you have a lone pair of electrons on the central atom, it's polar. The lone polar pair, lone pair polar. So I'm going to give you 2 to work on. I want you to do the exact same thing. I want you to do the Lewis dot structure, tell me what the electron geometry is, and tell me what the molecular geometry is. Let's do SO3 2-, which is also known as sulfite. And then pH3. Okay, give you 5 minutes to do both of those. So Lewis structure, Lewis structure, the electron geometry, the molecular geometry, and then tell me if it's polar or non-polar. All right, so this one over here, this is a polyatomic ion. The only place that we really treat it differently is when we're counting up the electrons. So sulfur has 6, oxygen has 6, and there's 3 of those oxygens. The last thing we need to do is take into account the charge. So if it's got a negative charge, that means it's got more electrons. So we're going to add 2 electrons to this. So 26 electrons to mess around with. Erase this thing here so we have a little more room. So I'm going to put sulfur in the center and my oxygens on the sides. Stick it together. Then I'm start working around. So outer guys first. So this one, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is 24 electrons. I need 26 electrons. So 2 more electrons. I can stick them right there on the central atom. Everybody is happy. Everyone has access to 8 electrons. The electron geometry is going to take into account all electron groups. So 1, 2, 3, 4. So that's tetrahedral. Doesn't matter where the O's are placed. No, if you would put like an O here and an O2 down at the bottom. This is a 3-dimensional structure, so I can always rotate it around to get to the shape that you have it at. Yeah, good question. So tetrahedral. The molecular geometry for this, we need to take our tetrahedral shape, and in this case, we've got 1 lone pair, so I need to rip one of them off, and so I get these 3 oxygens that are sort of pointing down. So that is trigonal being for 3. Whoa, trigonal being for 3. Pyramidal. Pyramidal because the lone pair is pushing down on them, so we don't get a planar shape or a flat shape. Polar or non-polar? Polar. Anytime you have lone pairs, it's polar. Deja vu over here, except in this one, we have 5 electrons plus 1 times 3, or 8 electrons. P in the center, H in the sides. Stick them together. That's 6 electrons. I have 2 more. None of these hydrogens want any, so I'm going to stick it on there. Ooh, very similar, huh? So electron geometry is tetrahedral. Molecular geometry is trigonal planar. A trigonal pyramidal here. Middle. These are same Z. Same Z between these 2. What else do we have? Polar or non-polar? This thing is polar. Lone pair right here, making it polar. All right. So hopefully that helped refresh your Lewis dot structure stuff. And not only Lewis dot, but also shapes. So that's really, if you can do this, that is a majority of chapter 10, majority of chapter 10. Other questions? Other areas you guys want to work on? We've got about 15 minutes left. We can mess around with whatever. Couple examples of endothermic and exothermic. Okay, in what sense, Gabrielle? Like with stoichiometry calculations, or because I'm not gonna have you like have to write an endothermic or an exothermic reaction. I would tell you that the reaction is exo or endo. If your delta, like physical properties. Okay, so endothermic reactions really the only thing that separates endothermic and exothermic reactions is endothermic will absorb heat and exothermic will produce heat. So this is totally hypothetical, but I'm going to say nitrogen plus oxygen comes together and produces NO2. Let's say that this is endo. It would have a delta H of reaction equal to plus like 86.3 kilojoules. meaning that it is absorbing energy to run the reaction. An example of a potential, and again, I'm making these numbers up, okay? I'm just really, the important thing is that you're seeing a positive for endo. Methane combusting to produce CO2 plus H2O. That's always going to be exo. Put a 2 there. 2 there. This would be exothermic. Its delta H of reaction would be, let's just say it's something like negative, I don't know, 235 kilojoules. Okay, so this thing is producing heat. This thing is absorbing heat. That's really the extent of endothermic and exothermic. Can we go over atoms, molecules, grams, compounds, conversion, a long conversion problem all the way to the end? Yes. So how many grams does 3.5 times 10 to the 25th NO2 molecules weigh? How many grams does 3.5 times 10 to the 25th NO2 molecules weigh? So I'm going to give you just 2 minutes to sort of go at it, and then I'll go over it because we're a little crunch for time. 2 minutes to try it out. Okay, so in this problem, it says how many grams of a certain amount of molecules how many grams does it weigh? So we're going to go from molecules of NO2 to moles of NO2, and then moles of NO2 into grams of NO2. Remember, moles is sort of our chemistry crossroads where everything kind of meets. So number of molecules, we have 3.5 times 10 to the 25th NO2 molecules. In order to go from molecules to moles, or individual things to moles, like atoms to moles, we have to use Avogadro's number. So 1 mole of anything, in this case we're dealing with NO2, is equivalent to 6.022 times 10 to the 23rd parts. So molecules, in this case, NO2 molecules. Then in order to go from moles into grams, we need to use the molar mass. So 1 mole of NO2 is, this is 46 grams NO2. So make sure your units cancel, NO2 and NO2 cancel, moles and moles cancel, and we'll be left with units just of grams. 3.5. Let's see. Big number divided by another big number. Make sure you're using parentheses when you plug that in, or your EE button. Times 46. All right, and I ended up with 2,673.5, and we're gonna round this to 2 sig figs, so 2,700 grams. Questions? Is that what you were looking for? Or were you looking for something else? Okay. Anything else? Anything else anyone wants to throw out there for the last couple minutes? A gas law question. If no one else has a question. Okay, yeah, we can do gas law. Let me think, sorry. Sometimes it's hard to come up with these just out of the blue. A gas at 35 degrees Celsius takes up 28.2 liters. What is the volume of gas at 46 degrees Celsius? 3 minutes. All right, just for the sake of time, so we can squeeze this in before the end of class. A gas at 35 degrees C takes up 28.2 liters. What is the volume of the gas at 46 degrees Celsius? So we're increasing the temperature. If we increase the temperature, I would expect the volume to also increase. This is comparing volume and temperature. So we're going to use Charles' law. I'm not going to test you that the name of this thing is Charles' law, but you do need to know that V1 over T1 equals V2 over T2. V1 is our initial volume. We have 28.2 liters. T1 is our initial temperature, which is 35 degrees C. Now, right off the bat, I'm just going to convert my temperature. 35 plus 273, because we don't want to get Celsius anywhere near these gas law equations. So add 273, and we end up with 308 Kelvin. V2, we're trying to find that. And then T2 is our final temperature, which we said was 46. Let's add the 273 to it. Plus the 273 is going to give us 319 Kelvin. So you can plug it in and then isolate for the variable. I kind of just like to isolate first. That's just how I go. So T2, we want to get V2 by itself. So T2 needs to move over to the other side. So do whatever the opposite is. So if it's dividing here, we're going to multiply it so it cancels, which means that T2 will go on the top over here. So final temperature, 319 Kelvin, times my initial volume, 28.2 liters, all over my initial temperature, which is 308 Kelvin. Kelvins will cancel, which we like, because we'll be left with just units of liters. So we take that 319 times the 28.2 and divide it by 308, and I get 29, 3 sig figs, so 29.2 liters. So our volume did in fact increase. Okay. So that's where we will stop for today. Really, this is our final formal meeting, but I am available next week. So if this time really works for you and you want to meet, or a couple of you want to meet on Monday, just send me a message. Otherwise, don't forget to take your test. I'll send a reminder email. Let me give myself a reminder to send you a reminder email. Yeah, and you all are good to go. Final will be next week as well. You're welcome, Lyric. You're welcome, Leanna. Thank you guys for being such good students, especially these 6 that showed up here. You guys have done really well this semester, so thank you. I appreciate it. I know it hasn't been easy. So yeah, shoot me an email. Enjoy your weekend. Start studying. Bye, everyone.